So the title here is Towards Coastal Flood Risk Prediction from Days to Decades. This is something I've been thinking about a long time. And I put the word nuisance in there, and Gary had a meeting not too long ago, and we talked very briefly about the word nuisance, and I think it's a terrible word. I agree with Gary. Nuisance makes it sound like it's a little annoyance. It's not a problem. Don't worry about it. It's a nuisance. No problem. But we heard yesterday from the city manager of Key Biscayne that on average, every home on Key Biscayne has lost $25,000 in its value, in large part to this nuisance flooding. If you lost $25,000, you probably wouldn't call it a nuisance. So we need a better name. I've heard people use minor. I also don't think $25,000 is minor. So if someone can come up with a good name, that would be useful. I'm hoping that the motivation for what I want to say today clarifies everything. Just the motivation itself of what I'm trying to do. And basically the part that Gary said is really, certainly the title part is really hard, but the other part that he said was really hard, the ocean-atmosphere interaction part, that's the part, the noise part, that's the part I'm obsessed with. That's the part that I like to think about. And it's motivated by going around and giving those kinds of climate change talks that Gary does, and I agree with him. These hostile audiences are much more interesting. I do, however, think that we do need to give those talks to the people that accept the science but need that ammunition so that, when they get in that fight with Uncle Bob at Thanksgiving, they got something good to say. So we have to do both. We have to do everything. But anyways, when I go out and give these talks about climate change, I get this question every single time. Every single time. People ask me, how often is it going to flood in front of my house next year, next month, 2 weeks from today? How often is it going to flood in front of my house? And so, I always decline to answer. I say, I don't want to make a forecast like that. It puts me in legal jeopardy, blah, 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 all this, I'm hedging. And the problem is this is hard to do. It's hard to make that forecast. And so that's what, so in my mind, Roger, by the way, this is sort of the definition of a co-production of knowledge, right? Someone keeps asking me the same question. I should be answering that question. And I kind of believe that in short order, when you turn on the TV and watch the 11 o'clock news and everyone's waiting for the weather forecast is going to start with the street flooding forecast. Where's it going to flood? 2 weeks from today or tomorrow or the day after, whatever. So we need to almost think about this nuisance flooding as, in many ways, a weather forecast problem. And so that you can sort of think of that as my motivation as I go through these slides, is that I'm thinking about how would I make a forecast, right, for tomorrow and out to a decade of, street flooding. And so I do want to provide a little bit of brief global context. Perhaps I don't need to, but it at least gets my mind, it's early in the morning for me, it gets my mind focused on things. And Gary talked a little bit about this, but I want to actually, these are the local drivers here in Miami. What are the local drivers of sea level here, and how does that translate into flooding, right? It's interesting because if you just predict sea level, you're going to miss part of the flood risk. So I want to point that out. And Nick Shea pointed that out a little bit yesterday also. He went rather quickly, and so it's not just the tides, it's not just the Gulf Stream, the atmosphere matters, there's a lot to be done here. So when we think about predicting regional flood risk, my contention is we have to include the trend, we have to include the tides, we have to include the natural variability, that is the atmosphere-ocean interactions, the noise that I'm obsessed with. That has to be part of the problem. And so this picture over there is just showing you I think it's Key West. Yeah, Key West is a nice long record of a tide gauge. It shows you the trend on top. And I don't remember why I put the ovals on there. But the bottom is the detrended time series. It's the detrended stuff, right? At any moment in time, when you're worried about that $25,000 in value of your home, right, that you're losing, you're putting it on the market, and the person who comes to your house and asks you, how often does it flood at your house? And you're worried about losing value. It's the noise. It's the noise that's driving down the value and how that noise evolves over time. So the trend, it's the combined effect of both of those. We can't do one without the other. Okay. So here's the global context. I just want to go back a little bit in time. And the top panel here are proxy records of sea level. This is from the 2013 IPCC report. It's showing proxy records of global sea level. And the point of that top slide is very simple. It's boring. Nothing's happening. It's flat. It's a flat line. That's the point. Over this, if you go back 400,000 years or many thousands of years, yeah, sea level has huge variability, but in the modern record, or close to the modern record, at least the last 3,000 years, sea level's been pretty steady. And that makes sense. We understand that. And it's not until we sort of hit the industrialization that we see this step function that Gary talked, some people call it a hockey, when we look at the temperature curves, we call it the hockey stick, but this rapid rise, and there's what's important, these messy curves, and the messiness and lots of data points and lots of error bars, that's important. All of that noisy stuff is important because that tells you just how confident we are in these estimates, that the sea level has definitively risen due to human activities on Earth. Okay? No debate about it. Gary talks a lot and does a lot of work using the satellite era data. So just showing you a picture, a global picture of the trend from 1992 through late 2016. This picture, to me, this picture is really important, right? We get this, as scientists, we get obsessed with looking at the global sea level. And from, if I'm a Key Biscayne resident, and I'm losing $25,000, I don't care what the global sea level is. I care less. I want to know what it is locally and how that relates to how many times it floods in front of my house, right? And this map sort of points to that a little bit. There's a lot of structure. There's a lot of details to the trend in sea level over the last, the satellite era. A lot of structure. And I'm going to show a picture in a second. And Gary likes to make fun of the fact that I do modeling, and yes, I'm guilty. I'm a modeler. And the next picture I'm going to show is, I hope it's the next picture. I haven't looked. Yeah. The next picture I can show, this was and is, and Gary's point that the models haven't gotten much better since the last IPCC report. This is a state-of-the-art global climate model assessment of sea level rise over that era. Okay, so to me, this picture, as a modeler, this picture really bugs the bejeebers out of me. It's not that it's wrong. It's not that there's not a lot of information in there. It's that it challenges our credibility. It challenges our credibility when I try to explain to people that, yes, we're confident that sea level is rising, and yes, we have lots of confidence in what the models tell us about sea level rise, but then I got to show this picture that doesn't look like nature. It doesn't capture the fidelity of nature. So there's going to be two things I want to talk about today as I go forward. The first is I'm trying to figure out, and it's a mess, and we're just getting started, I'm trying to figure out how can I make a weather forecast of flooding in your street due to sea level rise, winds, everything. I want to make a flood forecast for you. Someday I believe it'll be on TV. I'll be famous, I'll be on TV. This is our flood guy, right? The second thing I want to try to get to today is we can do much better than this. Much, much better than this. We're on the cusp of doing much, much better than this with our models. So those are the two things I want to accomplish today. So there's just a quick picture. This is it's very blurry. This is the relative change. So basically you can think about this as removing the global mean from that other plot, just to show you the relative change. So let's pause and think about regional sea levels. Or, my obsession, of course, is right outside here. And Brian is going to tell us a great story about today. I'm not going to give it away, Brian, but you're going to tell us today, right? Okay. So what's happening right now? Well, Brian's going to tell us. So anyways, what causes regional sea level? This is some work from one of my graduate students who's moved on and does risk consulting for a reinsurance company. Interesting. Anyways, the ocean and atmosphere circulation is a big component of this problem, particularly when you go on these relatively short timescales. And that's what this picture is sort of highlighting. In this picture, what Diane tried to do is she wanted to decompose that Key West curve, decompose it, going back in time and then going out into the future to the different components. And what you notice is there's a component that's due to ocean circulation on here. The component that's due to ocean circulation in all the curves that Gary talked about, that Billy Sweet produces, that NOAA produces, that's not part of the calculation. In addition to those tidal fluctuations, the ocean circulation, the atmosphere-ocean part is not part of those curves. And so you can see over a significant component going out into the future, you can actually decompose, you can actually start thinking about which part is due to ocean circulation. That's one important component. What I want to talk about is when we talk about days, weeks, season, next week is it going to flood at my house, the atmosphere really, really matters. The atmosphere really, really matters, okay? Particularly here. Some parts of the world it may not matter as much, but particularly here. And then, of course, as Gary pointed out, there's the two big dogs, right? How much does the ocean warm? We understand that's part of our human experience. You warm up a gas, it takes up more space, right? That's a steric effect. But also there's this mass, this volume that Gary's talking about. That's the ice melt. Greenland and Antarctica melted. One of the estimates is something on the order of 27. If both of those huge ice sheets melted, the estimate is on the order of 27 feet of equivalent sea level rise globally. So right here, we'd be in a little bit of trouble. Okay. Oh, and the land. We forget the land. In Miami Beach, of course, Miami Beach, I'm never going to get through my slides. In Miami Beach, in Miami Beach, the land is subsiding, and that's a big problem. You take a barrier island and you fill it in with debris, and then you build tall buildings on it. The fact that it's sinking is not a big surprise. We can't ignore that part of the problem. The ocean circulation part that Gary pointed out, it's from a physical sciences perspective, it's pretty straightforward. But if that current, the simplest way to think about that circle with the X in it, to think of that as this Gulf Stream or the Florida current running along the coast. When that thing's raging, it starts sweeping water away. That pushes down sea level. So strong Gulf Stream is a good thing. It's a good thing. If that Florida current or Gulf Stream weakens, then that ocean surface tilt reduces, and we have higher sea levels. So that ocean circulation part that might explain what's going on here locally over the last few weeks and months and years is a big part of the problem that we have to think about. I'm going to skip this one. Okay. So I'm starting to drill down locally. I talked about the mechanisms for local sea level rise, and I want to start to drill down. This is a report produced by Billy Sweet, who's at NOAA. He's sort of the NOAA National Ocean Service guru on sea level rise. And one point of confusion, by the way, in the world of climate is the use of scenarios, right? So to me, as a climate modeler, I use a scenario for CO2 CO2 concentration or emissions for the atmosphere. That's my scenario. I treat that as a prediction, right? That's a forecast of what the chemical composition of the atmosphere is going to look like going out into the future. I slam that into my climate model, and I make a prediction of what the future is going to look like. Those scenarios that's not what's intended. Those scenarios for CO2 emissions, CO2 concentrations, that's not what's meant. It's an economic scenario. It's a what if, right? And Gary pointed that out. He showed that low curve, that what if curve. What if we started reducing CO2 emissions and even became negative? That's a curve. That curve that Gary was griping about, that curve relies on technology that does not exist today and is unlikely to exist in the next 30 years, right? Okay? So the problem with the IPCC process is we treat those things as equally likely. And that's what Gary was complaining about. You put up those curves and you say the low scenario is equally likely, it's interpreted as equally likely as the high scenario. As a climate modeler, I treat them equally. I test them fully as if they're equal, the probability of them happening are equally likely. That's a problem with the IPCC process. There's a disconnect between how the physical scientists think about those scenarios and how those scenarios are produced and what they mean. That's a fundamental problem. Okay, that's my hobby horse. These scenarios, now this is yet a whole nother different, another scenario, and Obe talked about yet another scenario. So Obe is being asked to make rainfall scenarios, right? It's not a prediction of rainfall, but this is a what if for rainfall. These are what ifs for sea level rise, right? And so are we supposed to be treating them as equally likely? At any rate, these scenarios, this plot here, so those are the various scenarios that NOAA has produced. Gary talked about the low one that it's against the law now, Gary, we shouldn't be showing it. Thank you. The low one, these two plots here, these dot plots are interesting. They basically, the top one shows you what's the water level in every once in a 5-year kind of flood. How much, what the water level would be throughout North America, right? The water level, okay? And so those are 1 in 5-year floods. What that water is, the bottom panel shows you when those 1 in 5-year floods would happen, on the order of every other month, right? And so we're deep in the red in Florida. And the red here is, 2020, 2030, so we're there. We're basically there. Okay. So let me drill down to my motivation. I want to be famous on TV, making the forecast for whether it's going to flood at your house next week, okay? So how am I going to do that, right? The first thing, I got to get rid of that word nuisance. The first thing is I have to think about how am I going to make that forecast because I have a sense, and we actually know this, I'm going to show you some evidence, sea surface height, sea level or sea surface height is not necessarily a good predictor of whether it's going to be a flood. Okay, important point. What are the other possibilities? And what I want to harp on here is it's the atmosphere. Ocean circulation, of course, really plays a big role, but on these short time scales, the weather forecast time scales, it's the winds. And then in defense of the modeling approach that Gary tells me I'm wasting my time, I'm going to ask, can the models capture these relationships? So can I make a forecast? The guy that makes that weather forecast, how does he do it? How is that weather forecast made? It's made by a numerical weather prediction model, the kind of models I play with to make climate forecasts. So can the models produce weather? Yeah, they can. That's how come the weather forecast guy makes a forecast, and I'm arguing the models can make a forecast of flood risk. Okay? So, whoops. Okay. So this is an interesting curve. This is, again, produced by Billy Sweet. And these are shifts in the probability of the water level at tide gauge stations. And the black curve on there that you can barely see, that's the overall probability. It's the overall probability. And the red curve is due to this phenomenon called El Nino. Okay? So I'm sure just about everybody in the room has heard about El Nino. On the West Coast in San Francisco, right, when there's an El Nino, it's on the West Coast. El Nino, from an oceanic perspective, is centered in the tropical Pacific. It spreads along the coast of North America, and then you get increased flooding. I grew up in Santa Barbara, and very near where I grew up, when there was a big El Nino, not only did our basement flood because of rain, but the streets at the beach would flood because of El Nino. There'd be a huge surge in sea level, and that would produce lots of flooding. And it's gotten worse over the years. We see an El Nino signal in Norfolk, Virginia. In fact, we see an El Nino signal all along the coast. And El Nino in the ocean, that kind of time scale is not propagating over into the Atlantic. So something else must be happening. And it turns out that it's the atmosphere. El Nino is producing a shift in the atmosphere that's affecting flood risk here on the East Coast. And it's pretty simple. So here's those two basic mechanisms. This picture is identifying San Francisco and Norfolk, and this is a picture from the 1997-98 El Nino. I was famous for 15 seconds in 97, 98. I was interviewed because I predicted the El Nino was coming 13 months in advance, and I was interviewed by a Polish Newsweek. So I was famous. And, it was in Polish, so I don't know if they got the quote right or not, but I was famous. So this is a picture, just a snapshot of what sea level looks like during a big El Nino. So you can see that huge rise in sea level in the deep tropical Pacific. That's El Nino, but that signal spreads all along the coast on the west coast of North America. You can see it spreading along, and that substantially increases the flood risk all along the west coast. On the east coast, it's a complicated picture. In fact, in Norfolk, Virginia, remember I showed you those curves, there's this big El Nino signal in Norfolk, Virginia. It's right at that node point. It's right at that point where the change is zero. The change is zero, right? So it's not sea level, not sea level. So this other picture, this is the winds. This is a shift in the winds. El Nino affects the whole structure of the atmosphere. Big signals propagate into the mid-latitudes, the whole circulation changes. Libby told us a lot about that yesterday. But we understand, we think we understand. We hope we can model it. So there's these big changes in circulation, and the big bold arrows are telling you what the changes are in the winds. So in Norfolk, Virginia, it's the fact that the winds are blowing onshore, persistently onshore, that's increasing the flood risk in Norfolk, Virginia during the 97, 98 El Nino. And we see those kinds of things happening today. Okay, so am I in trouble? 7 minutes. I'm never going to get even close. So, I'll grab each one of you individually and go through my slides. So, Virginia Beach, somewhere in Texas, and then San Francisco. I'm going to look at those three stations, and I'm going to think about this day's, weeks kind of forecast. So this is getting ready to do my weather forecast, right? So let's take Galveston Pier. So this is the raw data at the tide gauge station. So this is the non-tidal residual, right? So this is all the stuff that I've removed all the stuff that Gary's thinking about. Well, getting that tide right. I'm not even considering getting that right. I'm just looking at the noise. Again, obsessed with the noise. Can I predict the noise? Part of the noise, what this non-tidal residual, of course, is the climate change. So the orange curve includes that trend, right? And I'm not even accounting for potential nonlinearity in the trend, the acceleration. That green line is just a linear fit, and I'm going to remove that, and that's the blue line. So the blue line is truly what I think is just the noise, right? And I'm taking that blue line, and I'm relating that to what's going on in the climate system. So I'm relating that to what's going on in the climate system. So wherever there's bright colors, it doesn't matter if it's red or blue, just bright. More pronounced colors means there's a relationship. Okay? So you can see in the sea surface height, SSH, sea surface height, sea level, whatever you want to call it, that's part of El Nino. That east-west contrast, high in the east, low in the west. That's a little bit of the climate, a little bit of the El Nino signal, but honestly, it's not quite right. So it's not precisely El Nino. The second panel, that's the winds at the top of, in the atmosphere, in the lower atmosphere. What do the east-west winds look like? And so you can see there's a hot spot. There's a hot spot over the Gulf near Galveston, right? So the winds are important in Galveston. Not so much sea level, but the winds. And then you get a similar kind of hot spot due to sea level pressure. So the atmosphere and that noisiness, look at how noisy that blue curve is, that day-to-day flood risk is largely being driven by atmospheric circulation. Do the same thing about San Francisco. That really looks like El Nino, picture I showed before. Big signals in the wind, also huge El Nino signal in the surface pressure. And then if we go to Norfolk, Virginia, same kind of idea. Not so much a signal in the sea surface height at all, but the winds and the surface pressure are really showing you a big signal. And unfortunately, we have done it for Key West and Virginia Key, but I honestly didn't have time last night to put those figures in. So very similar kind of picture that here locally, the biggest signal is due to the atmosphere on these shorter timescales. So can the models capture these relationships? So this is an attempt to capture those relationships going forward 6 months in time. So this is using an evil model. This is a model that's used, it's exercised on an operational basis. It's a system that we use here at the university, but it's a product that we developed in collaboration with NOAA. It's now an operational system. It's called the North American Multi-Model Ensemble. And this model is making forecasts of winds and sea surface height and temperatures and everything. It's initialized with real data. And the question I'm just asking is, can the model reproduce the observed relationships 5 months into the future? So there's some parts of it that look okay, and there's some parts of it that don't. My argument is much like Libby, is I can dig in and start to take the sea level pressure, the winds, the sea surface height, all of those things, and construct a forecast of what the flood risk is going to be 6 months in advance. And I can do that in San Francisco. And of course, in San Francisco, the tool is going to be much more what's happening to El Nino, what's happening to the sea surface height, as you can see. And then this, of course, is Sewell's Point. I want to be very careful, right? So those are just, how are the ups and downs? I don't care how big they are, but how are those ups and downs related to the winds? I want to be a little more careful. I want to talk about thresholds when there's actually water in the street. And so NOAA, Billy Sweet again, has developed a technique to actually define what are those thresholds. What are those thresholds? And so this one I think is in, I think this is in Charleston actually. This is the number of flood days per year that have been happening since 1950 up to the present based on thresholds, based on a particular threshold. So can I look at the actual number of flood days per year? So this is looking at tide gauge data. Every, I can't remember what the frequency is, but very high frequency. Number of estimates per day, and how many times we cross that threshold. So I'm counting how many times we cross that threshold. This is over the long term. This is in Sewell's Point. We have a good confidence in the record. Trend noted on that. Over the near-term epoch, it's kind of a little bit harder to identify that trend, but it's certainly there. And then these are the atmospheric circulation patterns that go with that noisiness, that day-to-day flooding risk at Sewell's Point. And so yes, there are elements here that the models can actually predict. Okay. Now, there's no doubt Roger would pat me on the back and say, Ben, nicely done, good job, thanks. So we certainly need to figure out how we get communities and people to think about how to use this information. That's not trivial. And I think Roger's point about co-benefit in terms of adapting to these increasing flood risks, those things are things we really need to start thinking about biting off and what our role is in providing networks to do those things. Did you give me a signal? I'm done? I'm absolutely done. Okay. So, last figure, I promise. This is a picture of where I think modeling can go. Okay? This picture, the picture that doesn't look like Earth over there, that's the state-of-the-art IPCC class model. That's what we're using to predict the future. That's what we're using to make global sea level rise projections. You can see why I'm bothered by that. We have a credibility problem with that kind of tool. This other picture, this is what we can. This is really what we can do. It's hard. It's hard, expensive, computationally expensive. But we do have models. These are coupled models that are used for a climate change simulation. But it looks like the real world. So not only does it make my forecast more credible, right? I think it also makes my forecast better. And I'm going to have to stop there. All kinds of pictures that, you know, we've solved the world's problems. This is looking at predictions of I lied, didn't I? I lied. Yeah, okay, I'm going to stop.